In this video, we're going to discuss the methods that scientists use to separate mixtures into their individual pure ingredients. These techniques are all different from one another, but they share the common goal of exploiting differences in the physical properties of all the different ingredients so that we can ultimately separate them out. Collectively, these methods are known as separation methods. Let's begin with an overview of some of the topics we're going to cover today. First, we'll talk about a definition of what separation methods are in more detail. Then the rest of the video is basically going to be a review of some of the separation methods that you'll need to be familiar with. We'll start with the simplest one, filtration. We'll move on to a technique that's a little more complex, distillation, which comes in a couple different forms, simple and fractional. We'll talk about something used primarily in organic chemistry, a method known as liquid-liquid extraction. And then finally, we'll talk about something a little bit more complex, which is going to be chromatography. The equipment used to do these separations vary in complexity and cost. They can be as simple as a simple piece of glassware. This is something known as a separatory funnel. That glassware starts to get more complicated as we move into different separation methods. This is the equipment we would use to do a distillation. It's actually a simple distillation. And taking it even further, this equipment can eventually graduate into larger, more expensive machines. This device is known as a gas chromatographer, and it separates different gas mixtures into, again, its pure ingredients. All of these gadgets do the same job. It just depends on how complex the method is to get that job done. Our first step is a straightforward definition of what separation methods actually are. All separation methods that we're going to be talking about are going to involve a physical process that's used to separate the mixtures into their individual pure ingredients. Scientists use separation methods for a couple different purposes, the first of which can simply be the purification of individual chemicals. For example, we can separate crude oil into many separate products like gasoline, engine lubricant, and jet fuel. Likewise, we use separation methods for simple things like the purification of water, separating out the ingredients we don't like the taste of or might be harmful to drink. We can also use separation methods as tools for the identification of chemicals in a mixture. This is, for example, very commonly used in crime scenes where a certain substance is left at the crime scene. We'll use separation methods to separate that substance into its individual components with the hopes that one of those components will provide information as to who might have committed a crime. Next, we'll move on to how do separation methods actually work. As we've already mentioned, separation methods are all about physical changes. We do not alter the chemical makeup, the chemicals during the separation process. What we do in separation methods is we exploit the differences in those physical properties. And the end result is we want to have changes occur to one of the compounds of the mixture exclusively without affecting the others. And again, that's going to be due to the differences in those properties. We're going to reference back to this idea a couple times throughout the discussion, so please keep this topic in mind. So let's move on then to our first separation method, something very simple known as filtration. Generally, filtration is used to separate a liquid substance from a solid substance using a physical barrier. This physical barrier can be something as simple as a sheet of paper. The main goal behind the physical barrier is simply that the liquid phase can travel through the barrier, represented by these smaller green dots, whereas the solid phase cannot travel through the barrier. These larger particles are getting trapped in the actual paper itself. The end result is that the liquid travels through and the solid stays on top of the filter. If you've ever made your own coffee from coffee grounds before as opposed to a Keurig, you've seen this process happen. This separation method has its limitations. It only really works when you're dealing with heterogeneous mixtures. Filter paper is actually something we buy in these sciences, and it's sold with different pore sizes. Basically, pore sizes refer to the size of these tiny little holes that exist in the filter paper. A lot of times these pore sizes are denoted by numbers, 1, 2, and 3, with higher numbers suggesting smaller pore sizes or a finer filter paper. However, filter paper comes with other characteristics as well, which create other numbering systems. Generally speaking, the smaller the pore sizes, the smaller the holes in the paper, and as a result, the better separation of fine particles. The catch to this is that those smaller pore sizes often also means a slower filtration process. So ultimately, there's a compromise between how good of a filtration method do you want versus how much time do you have to do your filtering. Filtration comes in a couple of different forms. The simplest form of filtration that you've likely already done in your scientific career is something known as gravity filtration. This takes advantage of the fact that gravity is going to pull downwards on the liquid and eventually pull hard enough to push its way through the filter paper to collect on the bottom. Simple filtration activities work very well with gravity. However, once you start dealing with finer powders, the filter paper tends to clog, and this can take hours, if not days, to complete. If you're looking to speed up the process, the next form of filtration is known as vacuum filtration. Vacuum filtration uses a special flask and a special type of funnel known as a Buchner funnel. It creates an airtight seal on the flask, and then we connect this flask to a vacuum pump that ultimately pulls air out of the flask. This sucks air into the top of the flask and ultimately pulls the liquid through the flask very quickly. This filtration process can be done in a matter of seconds as opposed to the minutes, hours, or days it can take for gravity filtration. Vacuum filtration also has its limitations, but generally speaking, it's a faster alternative for filtration. Taking this one step further, just like any technique, filtration comes in much more complex methodologies. This setup down below is used in the filtration of water in a reverse osmosis scenario. You have larger volumes of the machine to allow for faster filtration processes, and you have multiple actual phases that the filtration goes through, each one removing more and more particles and more pieces from the actual water, making a purer and purer sample. Let's move on to our second separation technique, a process known as distillation. Distillation is unique from filtration in that it is used to separate homogeneous mixtures, mixtures where all the components look the same as one another. The property that we exploit to do this type of separation is the fact that these different components likely have significantly different boiling points. One will boil at a lower temperature, a second will boil at a higher temperature. If we think back to our heating curve from previous units, we can see that the boiling point of our substance up here causes a stop in the temperature change. At this particular part of the process, our change in temperature is going to be equal to 0. This is the part of the process that we're able to exploit. If our mixture then contains two different substances, one denoted by the red line and one denoted by the blue, what will happen is as we increase temperature on the scale here, eventually we'll hit the boiling point of the first substance. This first substance then is going to use all the energy to boil, preventing the temperature change, meaning we can't get up to the boiling point of our second substance. We'll get all of this chemical to boil first, having it evaporate into the air, leaving only the second chemical behind. When the blue chemical is finally all gone, then the temperature can start rising again, leading up to the second boiling point of the second substance. So as you can see, distillation can not only separate two substances from one another, but many substances, depending again on how different those boiling points actually are. The equipment used to get the job done is relatively simple. In this flask right here, we would have our mixture of substances. In this case, that mixture is basically a saltwater solution. We apply heat energy, and the heat energy basically gets the water up to its boiling point first. So that would be this lower boiling point. The water then evaporates and travels up this tube. Its measured temperature with a thermometer helps us keep track of what substance is boiling, as we know their boiling points. This gas eventually enters this device over here, which is known as a condenser, where we have cool water pumped in. That cool water causes the gas to turn back into a liquid. That liquid flows down the tube, down into a second container, and now we've purified our water. What will eventually be left in this container is simply just the salt that was not able to boil because of its significantly higher boiling point. Just like with filtration, distillation comes in a couple different flavors. This process right here that we see depicted in this picture is something known as simple distillation. We simply have the substance boiling at a heat source, it evaporates, cools here, and goes into the second flask. This process typically works when you have substances that have very, very different boiling points. However, when those boiling points start to become more and more similar, the process of evaporation starts to interfere with the process of distillation. Some of that second liquid is going to naturally evaporate even below its boiling point, and the end result is we won't get as clean of a separation as we want. For situations like that, we tend to use a new process known as fractional distillation. In fractional distillation, we have a very complicated column that allows the liquid to boil and evaporate and boil, condense and boil and condense and boil and condense and boil over and over again. Each one of those events causes the liquids to separate better and better, and the end result is we can get liquids even with similar boiling points to separate very, very cleanly. This is very commonly used in the separation, for example, of crude oil into its constituent components. The crude oil is heated in a heater. It enters this very large chamber here that has all of these surfaces. Each one of those surfaces is a place where the vaporized crude oil to recondense and then re-evaporate and then recondense and re-evaporate. And what ends up happening is as we travel further and further up the tube, the high boiling point stuff tends to collect down at the bottom. This is where, for example, we get fuel oil for trucks and lubricating oil. The low boiling point stuff tends to float up to the top. This is where we get refined gases and things like kerosene up at the top. And we can collect many, many different products from this one distillation process. As I mentioned, this process is a relatively large-scale thing. If you've ever seen an oil refinery, we see these large towers here, and these large towers are basically these fractional distillation columns or fractional distillation towers. The large size allows these companies to put a lot of crude oil through these things all at once and produce these different materials at a relatively quick rate. Next on our list of separation techniques is a process known as liquid-liquid extraction. Just like we were talking about distillation, liquid extractions are all about separating, again, homogeneous mixtures. But instead of separating them by boiling point, we're going to instead separate them by solubility. The two liquids will preferentially dissolve in one solvent versus the other, and as a result, we can use that as a separation technique. As a quick reminder, the idea of solubility is the ability of a solute to dissolve in a solvent, and it's typically determined by the types of intermolecular forces between the solute and solvent. The more of those forces exist, the stronger the reaction between those two substances, and typically the higher solubility we tend to see. Some quick examples of that is talking about salt and various solvents. Salt has a high deal of interactivity with water, therefore it has high solubility, whereas salt doesn't have a lot of intermolecular forces when interacting with oil, and as a result the solubility ends up being low, if not zero. Back then to liquid-liquids extractions, when we're dealing with an extraction, we're basically looking to have two layers of a liquid, and the two layers of the liquid do not mix with one another. We do this process in a special type of glassware known as a separatory funnel. This separatory funnel allows us to place our two liquids that don't mix together inside the main container here, and this valve on the bottom allows us to preferentially decant one of those substances off while leaving the other inside the funnel. This is basically how we're going to finish the process of a separation. So to demonstrate how a liquid-liquid extraction occurs, I have a little bit of an animation here that'll hopefully explain the process. In this separatory funnel, we have our two layers. This layer is a solvent with some sort of dye in it, producing the red color. This layer is a different solvent without the dye. If we want to separate this dye out and purify this solvent, what we'll end up doing is we'll take this separatory funnel, we'll flip it over, and we'll start shaking the contents of the separatory funnel. Just like mixing together salad dressing, the two layers start to interact and mix with one another. If the dye is more soluble in the lower solvent than the top, what will start to happen is it'll start preferentially dissolving in the lower layer and start leaving the upper layer. The end result now is that our dye has dissolved in the lower layer, leaving our top layer now purified. We would now open up this valve here on the bottom. That would allow us to pour off the lower layer containing the dye, leaving the now purified top layer with the dye removed. So let's wrap this video up then with our final method of separation, a process known as chromatography. Again, just like distillation and liquid-liquid extraction, Chromatography is all about separating, again, homogeneous mixtures, but again, we're exploiting a different difference this time. We're going to exploit how this compound reacts to two different types of chemicals, something we'll refer to as the mobile phase and the stationary phase. This is a much more complicated form of separation, and it comes in many different varieties depending on the types of materials you're trying to separate. So let's get back to those two phases we were talking about. The first of two we'll talk about is the mobile phase. The mobile phase is typically a solvent, and that solvent is something that our mixture that we're looking at tends to dissolve in relatively well. This mobile phase, as the name implies mobile, travels through our separation device, something we'll talk about in a moment, known as our stationary phase. The stationary phase, then, is typically a solid material. It stays in one place, and the mobile phase travels through it. As a result of this, the different ingredients of the mixture are attracted to the stationary phase, but they're attracted to the stationary phase differently. Some of the components of the mixture are attracted very strongly, others are attracted relatively weakly. The more strong the attraction is, the slower the substance is able to move through the stationary phase. The less attraction to the stationary phase, the faster the substance moves. As the material then moves through the chromatography medium, the stationary phase, the faster stuff goes front, the slower stuff stays to the back, and our mixture, again, now becomes separated. The simplest form of this process is something known as paper chromatography, something we'll likely have the time to be able to do in class. We start this process by taking a paper. This paper itself is our stationary phase. And then we add a solvent that we dip the paper in. This is our mobile phase. As a result of being dipped in the liquid, what's going to start happening is the mobile phase is going to start basically getting absorbed into the paper, and it's going to start moving up the stationary phase. This dot is the chemical mixture that we want to separate. As the mobile phase comes in contact with the dot, we can see the dot starts traveling up as it interacts with the mobile phase as well as the stationary phase. By the time we get to the end of the process, what we can see is that what once looked like one color of ink here separates into a couple separate distinct colors. This blue color up here interacts mostly with the mobile phase and travels through the stationary phase very quickly. This purple color here to the bottom is much more attracted to the stationary phase, and as a result is stuck on the paper a little bit more, and it can't travel quite as quickly as some of these other colors do. The result is the distinct separation of these three separate materials. Chromatography comes in a lot of different flavors and varieties, as we already mentioned. We already saw a quick demonstration of a very simple method, often used in classrooms to demonstrate this, something known as paper chromatography. Something you probably saw back in freshman year is a gel electrophoresis. It's a very simple methodology that's the same basic principles. Instead of using a mobile phase that's attracted via capillary action, basically, gel electrophoresis uses electrical currents. Gel electrophoresis uses electrical currents to pull charged DNA samples through the gel. The gel has certain size pores, and bigger DNA samples get stuck in those pores, i.e., they interact with the stationary phase and they can't move quite as quickly. That creates this telltale separation of lines, each one representing a different snippet of the DNA that you put into this mixture. Another form of chromatography is known as HPLC, or high performance liquid chromatography. What this does is it uses a large column of a powdered chemical and has a liquid pushed through it at very, very high pressures. What this is actually for is less about identification and more about purification. We can put a lot of chemicals through this column, and we'll collect the products that come out at the other end as purified substances. Last but not least, but certainly not the end of the list, is something known as gas chromatography. Gas chromatography works the same way as HPLC. We inject a small amount of gas into a long tube that's heated in an oven. As the gas travels through, some of the gas particles stick to the chemicals in the tube, other of the gas particles simply travel through. By the time these chemicals get to the end of the gas tube, the end result is some chemicals go through quickly, other chemicals go through slowly. We're able to detect those, and we'll have a computer basically plot points on the graph to show us when each of the individual chemicals came out. And that brings us to the end of our discussion. At this point in time, you should be able to explain what separation methods are typically used for. And you should be able to also briefly explain for each individual separation method what types of mixtures they're capable of separating and how the methodology works and what property is exploited for each separation. And you should be able to do that for filtration, distillation, liquid-liquid extractions, as well as chromatography.